time, tap in. Oh, great. Thanks, Veronica. Looks like you're recording. Okay. Or if you let the 10:30 submission time arrive before your 50 minutes is up, then what will happen is the exam will self-submit, and anything that you've typed on the web page but have not saved will be lost. So I want to remind everyone to click save or to click next page or previous page or table of contents, all of which also save at the same time as you click them. And just click those as often as you can while you're taking the test. And if possible, when you see that your 50 minutes or 10:30 is almost up, it's a good idea if you yourself click submit for grading, and that'll ensure that anything that's on your page will also get saved and processed. All right, so that's what I wanted to add about that.
Very good, very good. Yeah, so save it, please, because otherwise then there's nothing we can do about it after you've done it. So, okay, so let's see. This was about the past. Let's see what we have to do now going on. So here for this week, there was the midterm. So we have lecture 12 and lecture 13 to cover. So let's go immediately to see the topic of these two lectures. So lecture 12 speaks about forces. Forces are felt physically as push or pull, right? So what is important to remember is that is a vector quantity. So because it's a vector, it has a magnitude and direction. Example of forces, you know, one is weight. We have already seen somehow gravity. So we will see how weight is related to gravity. And then we have a tension when you have a force on a cable, normal force, which is something maybe new for you. So it's the supportive force of a surface, and friction. We already know what is friction. For example, the resistance of the air, the resistance of the soil, and so on. Then we also have a spring, which is a sort of restoring force, and many other. So for the weight, you see that the weight is always going downwards, and is mass time acceleration, the equation of a force. So in this case, the acceleration is gravity, so mg. M, the mass, is a scalar value, so it's not a vector, but because g is a vector, the force will have the same direction of g, while the intensity, the magnitude, of course, will be the magnitude of g multiplied by the magnitude of the mass. Then we have tension. We will see maybe later in one example. So the tension is always along the cable, and is indicated with this T. Like this we can understand, or with a capital T. And then we have a normal force, which is indicated with a small n here, or a big N, that is always perpendicular to the surface. So no matter how we will see later in examples, but always perpendicular to the surface. So the Newton's first law, or law of inertia, says that an object in motion remains at constant velocity, and an object at rest remains at rest unless acted upon by a net outside force. So we kind of already saw that when we were saying, remember when we saw the free fall, the parabolic motion. Sorry, I have a construction people here in the house. So if you hear noises, are them that are hopefully not destroying my place. So we already saw when we were looking at the parabolic motion, for example, when the velocity was equal to 0, but also in the previous examples, that to change the velocity, when the velocity was 0 or constant, to change the velocity, you needed to apply an acceleration, right? So now we know that acceleration is associated with a force, because force is mass time acceleration. So of course, we know that now from the first law that a body, an object, remains at rest or at constant velocity unless there is an outside net force, which is different from 0. So you might have not only just one force, but multiple forces that are acting on your object. And so in this case, it needs to be the sum of all the forces that needs to be different from 0. Then going on, it's a bit slow, sorry. So, the Newton's second law, let me go from here. The Newton's second law is giving you okay, is here. Okay, it says that the sum of the forces is equal to mass time acceleration. So essentially, if you have only one force, you have F is equal to ma, but if you have lots of them, you have to sum them up. And you say, how do they sum them up? Of course, they are vectors. So you have to take into consideration all the components along X and along Y. And we will see later. So here, what concern the units, mass is always measured in kilograms, in MKS units, while the acceleration is meter per second square. Now, this is a pretty long way to express something that we use it so often. So because of the inventor, the person that discovered the force is Newton. So, and that gave these mathematical equations. The unit of the force is called Newton. So it's measured in Newton, in the MKS units, while here you have the other units, okay? So remember, Newton is always mass time acceleration, so kilograms multiplied by mass divided by second square. Now, we say that acceleration and forces are vectors. So, of course, you have to do what is called the free body diagram. So you have to put together all the inventories of the forces, choose the coordinate axis, and we will see that this is very important that you do it in a smart way, and then consider all the components and find the components along X and along Y. And to find the total force, you will have to sum up all the forces along X and the forces along Y and see what's going on. Then Newton's third law says that to every action there is a reaction, okay? And if we want to speak about something that is more physical, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So if you are pushing the wall is pushing back at you. So you have a reaction. So if you have that you are A and the wall is B, you are pushing with a certain force AB, and the wall is going to push you with the exact same force in the opposite direction, so that none of you essentially moves. You are stuck there. So all the forces come in pairs, but the action and reaction forces act on different bodies. And so here it says, for example, you cannot touch without being touched in return. Already the feel that you are touching something is because something is touching you, right? So the force here exerted on hand by the desk is equally opposite to the force that the desk extends to you. This is your force. You are pushing the desk, so the pink one, while the violet one, this one, is the one exerted by the desk, opposite to yours. Oh, it's more difficult with this thing. So for example, let's see this. This you have a statue. For the statue, what you see, we have gravity, the weight of the statue. So mg, which is always going downwards, right? And then you have here the normal force, which is opposite and contrary. And the normal force is always perpendicular to the surface. And since here the surface is in this direction, the normal force just goes up. And so the net force here is equal to 0 because, of course, they have opposite. So if you sum up, one of these forces is positive along y, the other one is negative along y. They have the same magnitude. If you sum these two, the sum of these two comes to 0. This was lecture 12, while lecture 13, I think it was just, let me see. Okay, for lecture 13 is a sort of a review of what we already said. So Newton's second law, the sum of the forces is equal mass times acceleration. So you have to separate the equations along x and along y. Please remember that, to do that. And then I think we can probably go to the problems and see some problems and examples together. So let me stop share this. And let me share, instead share this one. Okay, so here is just a few examples that I wanted to show you. For example, let's start from this one. Yeah, let's start from this one. So you might have, that's why we need to consider the sum of the forces, because you might have several forces acting on an object, right? So when you have something like this in your problem, the first thing you have to do, you have to put everything in a point. So all the forces, you need to condense them to a point, essentially. And after that, you have to put all of these forces together. If you leave them the way they are like this, it's just confusing. You cannot understand what is going on, right? So you want to put all of them in a point. And after that, you say, okay, what do I have? I have force 1. Let's start from 1. Force 1, which is going downwards in this direction. So x and y, we are going to have F1 going in this direction, where here we have 60 degrees, okay? And actually here is from the book, but what you should do, instead of getting y and x like this, I mean, it's just to show you, but in the reality, you have to take the y-axis going up here towards the normal and the x-axis going here, okay? So in this case, we are going to have F1 60 degrees below the x-axis, okay? Then we have F2 going 30 degrees, again, downward. So I have to put everything attached to this point. So 30 degrees going down, 30 degrees below, again, the x-axis, but in this direction. Then what we have the weight of the object. The weight of the object goes down towards the y-axis, going down. This is gravity, mg, okay? And then we have the normal forces that goes up, okay? So along the y-axis. Because I need to decide where I want to put my x and y, the smartest thing is to do it x along this axis here and y along this axis here. So you see that here you are going to have to enjoy to find all the components. And if we want later on, we can do that. Let me show you another example. For example, here we have a dog that is carrying a sled. And again, in the problem, you are going to have this picture. But with this picture, you don't want to work on this one. So what you want to do, X and Y, again, I do a dot or I do a box just to indicate this box is my object. And then I said, what do I have? Which are the forces playing a role here? I have the force of the dog, which is going in this direction towards the x-axis. And then what do I have along the y-axis? Because remember, they are vectors. So every time you will have to consider the x-axis and the y-axis. Along y, what do I have? I have the weight of the sled. right? So the weight, because of gravity, goes down. And so I'll put it here. And then what I'm going to have is the normal force, because it's attached to the sole. So the normal force that goes up. Okay, so for the Newton's law, what I'm going to write, I want to find the forces along the acceleration along x. So what I need to do, I need to write the sum of all the forces along x. Do I have any components of the normal force along x? No, right? Because everything is along y. So I don't have anything. The component along x is 0. Do you have a component of the gravity along x? No, it's all along y. So 0 plus fx equal to max. So ax is going to be fx divided by m. So depending on what is asking the problem, you're going to have different thing to solve, but the equation that you're going to use is going to be this one. Along y, let's see, along y, is the dog applying any force along y? No. So the dog, the component of the force of the dog is so, sorry, I need to close the door. Let me close the door.
I just want to say it's we have to be careful here because F here is the force from the dog, even though it has no subscript on it, right? Or you can think of it as the tension in the cords.
Yes, F
that,
is the force
yeah.
of the dog. Yes,
Yeah,
or the tension in the cord.
So
Exactly.
this is actually the X component of the dog's force and the Y component of the dog's force.
Yes. So here what do we have? Along Y, we have normal force that goes up. So it's positive because we choose the y-axis being positive in this direction. So this is positive minus the force that is going down, gravity, because it's going in the opposite side of the y-axis, plus 0 because the force of the dog is all along x, equal to ma along the y-axis. Now, here you see that this one is going to be equal to 0 because in the reality there is nothing, no motion, nothing going on along the y-axis, right? So I-axis, this ay is going to be 0. While along x, the dog is actually, so the sled is not flying, it's not pulling the sled up or down. The sled along y is stable. It's along x that is moving. So all the motion is going towards x. So max, the component of the acceleration along x, is different from 0, okay? So there is no y direction motion. So that's why here is 0, while we have the motion along x. So that's why this component of the acceleration is different from 0. Am I going too fast? I don't know if there are questions that somebody wants to point out. Otherwise, I can go to the next problem. Let's see the next problem. Let's see this next problem. So next problem is very similar to this one, but we just have a bigger dog, or instead of a taller dog, let's put a horse here. So the direction of the force along the rope here is different as an angle. You see, before it was all along x, now we have an angle. So here he also gives all the information about this problem. So let's read it. During your winter break, you pull, actually it's you, it's not a horse instead of the dog, is you pull a rope attached to the sled by a force of 150 Newton at 25 degrees above the horizontal. So you see how these equations will be different from the previous one because we have this flip, this angle. The mass of the sled rope system is 80 kilograms, and there is negligible friction between the sled runners and the ice. Find the acceleration of the sled and find the magnitude of the normal force exerted on the surface by the sled. So let's see. Again, here we have to consider, we have this drawing. Let's start from the beginning. We have this drawing. From this drawing, we have to come up with something like this. If you work on this one, I'm telling you, you're going to have problems. I'm having problems. So for you, that is the first time, I don't expect you to do better than me. So you have to really put everything here, Y and X, and then you are going to have your dot, which is going to be your sled. Here is the force on the rope, because you are pulling the sled. And again, we have gravity and the normal force. The only difference with respect to the problem of before is that here you have an angle, and this makes some difference. So again, we look at X and Y component. Along X, what do we have? We have normal force. Do we have any components of the normal force along X? No. Do we have any components of the gravity along X? No. So the only component of the force along X is actually the component of this force, which is F cosinus of theta. And we know this from trigonometry, right? So it's this component here. And this one is equal to MAX. Is this acceleration different from zero? Yes, it is, because we are pulling the sled, and so probably if the sled was stuck with zero velocity, V equal to zero, if I pull pretty hard, that velocity will be different from zero, and the sled will start to move, which means there is an acceleration. So, and is actually what I'm looking for. So here I can find acceleration along X is F cosinus of theta divided by the mass, where again, this Ft cos theta is the component here. Mike, if you could also draw the components of Ft along X,
Sure.
so we can see it. Thank you, super kind. So is this component of this force along X, Ft cos theta divided by the mass. So do I know Ft? Yes, it's given 150 Newton. Do I know theta? Yes, given cosinus of 25. Do I know the mass of the sled? Yes, it's given. Very good. Equal to what? Here we have Newton. Here we have an angle, so we don't have information about we don't have dimensions. So Newton, if I divided the Newton by kilograms, what I have left is meter per second square, which is actually the unit for acceleration. Very good. So I'm good with that. Let's look along Y. Y, what do I have? I have normal force. Remember, we saw it even in the examples of before, along Y. It's all along Y. Gravity, yeah, it's going down and it's minus mg. Very good. Before it was equal to zero. It was ended there because all the force was along X. Here instead we have the components of this force along the Y axis. The components is according to trigonometry, Ft, which is our force along the rope, sinus of theta. And this is equal to the motion along Y. So M, the force along Y. So MAY. Do we have any motion along Y? No. Again, sled is not flying. So it stays attached to the ground. So the motion along here was zero and it be keeping zero, being zero. So this is equal to zero. So I can just write that here I'm looking for the normal force. So I'm looking for the normal force. I take out normal force is equal to mg. I bring this in the opposite side of the equal minus ft sine theta. mg, I know m 80 kilogram, g 9.81 meter per second square, minus ft 150 newton, sinus of 25. I do all my calculations and I find 720 newton. Here I have newton plus I have an angle, so no units. This is newton. Here I have kilogram meter per second square, which I know is newton. So yes, I can do 80 minus 150. So I can do this calculation and find 720 Newton. Is this okay? So let me know if I have, if there is something from the chat that needs more attention. And so
yeah, so one of the students was asking, is FN the same magnitude as FTY, the Y component of FT? The answer is no. I'm sorry, I just happened to draw that little FTY, so it looks the same way. That's an accident, right? That's a coincidence. So FTY,
yes, FT might have been completely different. Draw an FT that which is going very up, and you'll see that is different. Imagine an FT with a 80 degrees here instead of this theta so small, much bigger and very long one. So no, the component of the FT along Y has nothing to do with the normal force. The normal force is related here to, is the opposite of the gravity.
And the normal force is initially unknown, and we solve for it using this expression right here. And that's how we get what the normal force is equal to. The sum of these three needs to sum to 0. That's all we do know, right?
Yes.
And we know 2 of them, and the normal force is not known, and that's actually what's being solved for here.
Yes, the normal forces is gravity minus the component of this one, of the Y component of this, which makes sense, right? Because the normal force you have to feel like is the reaction of the surface to what is perceived. And so it could be to your weight if you are fully attached to the ground, or it could be a bit less if there is maybe somebody that is pulling you a bit up. So in this case, there is the rope that is kind of pulling a bit the sled a bit up because of the rope, and so the perception of the surface is that actually the sled is a bit less weight, has a bit less weight. Does it make sense to you? I hope. So let's see. If you don't have other questions, am I going too fast? Maybe I'm going too fast. I don't know. The fact that everything is on Zoom is so complicated. We don't get the direct feedback from the students. So here I just put this drawing just to show you that in the reality, we always select, so far, we always select X and Y in this direction, but there are cases where we might want to choose a different reference system. So for example, in this case here, you can decide X and Y going along this direction. So here you see the normal force is no more going like before, straight up. Is always, you need to remember this, is always perpendicular to the surface. While Mike, since you are so skilled with this thing, are you able to draw gravity here, please? Because
am I able to what? Sorry.
To draw gravity.
Oh yeah, sure.
Gravity. Because this is always a misconception that people have. They think that the normal, at some point, they think that the normal force is always opposite to gravity.
Should I use him should I approximate him as a point mass?
Yes.
We do that? Okay, all right. So like the previous two slides that everyone saw, we're gonna draw all the forces acting on the center of his mass. So here's the normal force now coming out of
Yes.
the hillside.
And
I
you
mean,
see
there's lots
how
of ways to write it that way.
And you see how it's tilted. And why it's tilted? Because it's perpendicular to the surface.
Yeah.
While this is
I just took this vector and moved it up there. Right?
Yes, this is gravity. You see that is going down. So gravity, no matters how is the surface is, if you are going down the hill, up the hill, doesn't matter. Gravity always goes straight down. The normal force instead depends on the surface. You need to pay attention to that, otherwise you might have problems. The normal force is always perpendicular to the surface. So if I go downhill, if I go uphill, if I'm in a flat situation, it changes. Yes. While gravity always goes down. So
by the way, when we sum these two force vectors, what direction is the sum, right? These are the only two forces acting on this snowboarder if we ignore friction.
Yes.
Yeah, so can everyone sort of mentally put those two vectors tip to tail? When you do that, what direction does the sum point? Does the resultant point? Looks to me like if I take the normal force and put it down here, right, then the sum is going to point this way. There, that's the sum. So guess what? The skateboarder is going to now accelerate down the hill.
Yes.
I'm sorry, I said skateboarder. Snowboarder.
Snowboard. Yes. And now is just the time for snowboarding. I don't know if you have any plan for spring break.
Chloe.
Skiing, but it's a good time. So
oops.
No, you were too fast. I wanted to say something also here. So try to, I want to show them, if you just do the axis, the normal way we do.
Yeah. So you mean with y upward?
Yeah, X and Y, the normal
horizontal.
way. How we normally do. So with the y-axis being opposite of gravity and x-axis going towards, yeah.
So this is what we normally would choose for most problems.
Yeah. And so in this case, if you use this axis here, you're going to have gravity all along the y-axis. But then you're going to have the normal force that you're going to have two components.
That's right.
Yes.
Right. The normal force has two components.
Yes, with the two components. While if you use the one that is indicated here, this one, you have the y-axis is, the normal force is all along the y-axis, right? And instead, you have the two components of gravity, one along x and one along y. So as you see, it depends. It's up to you. I mean, as long as you are consistent, you could decide both of those. The one here or the one there. So the one here, you will have, as we said, gravity going down, and then you have the component for the normal force along y and along x. This one, you are going to have all the normal force all in one axis along y, and then you are going to have the gravity, you're going to have two components.
Veronica, if I could add on one point here. When we, in lecture 15, we do some inclined plane problems. So that's actually coming. And our textbook prefers this tilted axis for inclines. And the reason is that the only advantage is when you add friction also,
of course,
then friction ends up lying exactly along the x-axis. So it helps your math simplify a little bit in that case. Yeah.
Yes.
So everybody, you're all going to see this tilted axis thing being used in lecture 15.
Yeah, because essentially, if you're going to have more forces along x, then it makes sense to use this, right? But you will see it later. So me, I prepared also a problem that it was with an unloading track, but maybe this is too advanced, right? I should wait then. What you think?
Maybe that's a good question. This could go with lecture 15 instead. Let me see
Yeah.
here.
So I could just do one of your problems.
Yeah, okay. Yeah, sounds good. Maybe we could bring this one back
We bring this one back, yes.
next week. Yep.
Let's not overwhelm our students more than what they already are. So let me go back. Where is? Okay, here, share. Okay, so let's just see one of the problems in this 10 minutes that we have. Do you have any preferences for these problems?
I'll just say this is what my handwriting normally looks like.
It's very good.
And my iPad looks terrible, right? So my iPad makes it look like I'm writing with the wrong hand or something. Yeah.
So
Makes it look like I had a stroke.
no, this is very good. So this is very similar. You see this one is very similar already from the free body diagram. You should be able to see that it's very similar to the one that we just did. So you have gravity going down, normal force going up, and then you have the force of the rope here with a certain angle. So this is essentially very, very similar to the one we already did. It probably only changes what is asking you to find and the numbers.
This is a problem everyone should know for midterm 2.
Yes. Those are very important things.
And
So
this
I
problem.
want you to be.
Both of these. Yeah. Both.
So let's do this one, which is a bit different. So in this case, let's see. Show here is a side view of an 80-kilogram desk resting on a tiny frictional wheels, not shown. A person pushes on a desk with a force of 250 Newton at an angle of 35 degrees below the horizontal, as shown. Predict the magnitude of the normal force from the floor will be greater than the box weight, equal or less. And then B, find the acceleration, and C, find the magnitude of the normal force. So if you look at this like that, you're just confused. So you cannot really identify anything unless you put all your forces. So here we have the force of the person that is going down, the normal force which is going up, and gravity which is going down. Now, Mike, if you don't mind to add also what I normally do, because I think it's very useful for the students, instead of just looking at this like that, just making that everything goes away from one specific
point, right? So we treat the desk like a point mass. And we draw all the forces.
Yes.
And let me just say this to everybody, that for physics 151, that will always be okay, right? If we were going to become civil engineers or mechanical engineers and do more complex problems, then if you had forces acting on different ends of an object, then it can result in a twist, right? Or a torque.
Yeah.
And then you have to be careful about exactly where on the object the force acts on average. However, for physics 151, that's
for what they do is
not an issue. We can always do this, what Dr. Bindi is suggesting. We can always pretend that the whole desk is a dot, right? A very massive, very heavy, little tiny object. And we're going to just put all of the forces acting, pulling and pushing on that one dot. So there's the weight or the gravitational force. There's the normal force, like this.
Yes.
And again, you can use different abbreviations. Our textbook likes to use little n and little w. Other books use capital F, and I like to use capital F for everything. And then there's the person pushing like that.
Okay. So if we do that, we already see, and then are you able also to do maybe in blue X and Y, the X and Y axis?
Sure. Yeah, the axes. Yeah, let me put the axes on. Sure.
Now, after we see this, we are like, okay, the Y axis, I definitely want the Y axis going toward the normal force and gravity, right? Okay, that's awesome. And so you already see from here that what you have, if we go, well, we can go here on the right and see that, yeah, we have for the normal force, nothing along the x-axis, and for the gravity, again, nothing along the x-axis. We have everything in the y-axis. So we have normal force going up minus mg, which we know is going down. And then what do we have for FP? For FP, we have the component of FP along X, which is FP cos theta P, and the component of FP along Y, which is FP sin theta P. Very good. So we just have to write the equation now and write FPX plus FNK plus, NX plus FGX equal to MAX, which are all the informations along the x-axis. We already see these two are equal to 0. So from this, you can find easily the acceleration along x. You solve putting all the numbers, dun, 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 and you find which is 2.56 meter per second square. The fact that it's positive, what does it mean? So if you got the negative number, means that it will go towards the left. Because it's positive means that the acceleration goes towards the right. And we expect that. If you have a desk and somebody's pulling it from here, you are expecting that the desk will move towards right. Very good. So now vertical, we have the components along Y. We don't have any movement along Y, any motion along Y. The guy is not trying to pull up the desk, is pushing it in a certain direction. So here, Y, M along the acceleration along Y is 0. So the sum of the components along the y-axis are all equal to 0. What do we have along the y-axis? We have our component of the force of the guy that is pushing the desk, the normal force, which is the reaction of the floor to the desk, minus mg, which is gravity. Okay, this needs to be equal to 0. So the normal force is equal to mg, when you move this in the other side of the equal, mg minus fp sin theta p. And so if you put all the numbers here, you're going to find this force at the end. So here, the component, where is, we don't have it anymore. But anyway,
Sorry,
the
I erased it.
component of FP is negative because, here it is, yes. The component of FP is along Y is negative, right? Because it's here. Are you able to make the component FP? Make it.
Yeah, I think I can do that. Mix it in blue.
So it's going, you see, in the same direction of gravity. Right? Yes, it's the blue one. This is going in the same direction of gravity. Okay. So it's something negative because we know that the y-axis goes up. So it's my sinus of minus 35 degrees, which comes something like that. Okay. So very good. Very good. So I think, are there questions, particular questions that we need to address in the last 3 minutes?
So this is what we mean by a 2D dynamics problem, when you have to solve some stuff in the x direction and also solve some stuff in the y direction, right? To fully describe the problem, right? Maybe get the acceleration of the object, or maybe get the normal force, things that are unknown.
Yeah, so there is here, so if y component of FP is negative, Fn increase in magnitude, yes, because it's like you are pushing. And indeed, you see, this is gravity, 784 Newton, while you end up having a normal force, which is 927 Newton. Like the weight of the desk will be actually bigger, right? Than the real weight. Mhm.
If you
Yes,
were to put a scale under the desk, the scale will read the normal force from the floor.
yes.
Yeah, not
It will
it's kind of
be
weird. We don't have a direct way to probe the weight of an object. All we can do is create things like scales that will read out the normal force between the object and the surface. Or
Yes.
sometimes we have hanging scales on springs, right, that tell you the spring force.
So weight is Fn. Well, weight, what we call
Technically
weight,
not.
is always gravity in this case. So yeah, is
Weight is Fg. This is
yes.
Oops.
Weight is what we call Fg, but the apparent weight is what is perceived by the surface. This is the normal force.
That's a good way to put it. It's the apparent weight. Yes, the apparent weight.
It's the apparent weight. Okay, so I don't know. Is there any other thing? I think we have 1 minute.
I guess I guess our time is up.
I guess happy Aloha Friday to everyone.
I'll just remind everyone that we have LAs at this Zoom address between now and 1:30 p.m. So once again, you can always check our LA schedule right there and drop in for assistance later.
Perceived weight and apparent weight, no, are the same thing. Is the real weight of an object, which is something different. So the weight of the desk is different. But if you push on the desk, then you are also pushing. The weight is the one related to gravity. The weight is you. You get into the scale and gravity is pulling you. So this is the weight. But if I get and I push you down or I pull you up, the scale is going to read the apparent weight because I'm also applying some forces. So it's not going to be only gravity, you know, that makes sense. Okay, Yuna. Okay, that's cool. Bye, everyone.